Okay, we're going to start section 5.5 today. We're going to be looking at how to factor polynomial expressions. I know in the previous chapter we had spent some time on factoring quadratic expressions and quadratic equations, but we know when we're talking about polynomials, well, now our expressions don't just have to have x squareds in them. We could have a variety of exponents. And so some of this today is going to sound familiar, but you are going to get introduced to two new types of factoring problems. And so the thing that I just want to kind of emphasize with you that we always sort of highlight when we talk about factoring is there is this initial step that you want to make sure you're checking these things. One, you want to make sure that all of your terms are in descending order. Two, you want to make sure that the lead coefficient is always positive. Remember, if it is not positive, you can make it positive simply by factoring out a -1 like a GCF in front. And then this is extremely crucial. We always want to make sure that we are checking for a greatest common factor. That's going to be key. You're going to notice that in a problem where you thought that you couldn't factor, once you remove a GCF, there is more factoring that you can actually do. Okay, so we always want to be checking for that GCF on the front end. Okay, once you've done these things, then the second step is then to see if one of your problems fits into one of these types of factoring problems. I think that this should probably be the letter G there. Okay. All right, I think sometimes we try to put the cart in front of the horse and we look at our problem and we're trying to figure out like which type of factoring problem it is when we haven't actually removed a GCF first, okay? That is going to be most students' problems is that they have not checked for that initially. Now, most of these should sound familiar. The simplest type of factoring problem is when you are able to remove a GCF, but then whatever remains behind, there's nothing more you can do with it, and so pulling the GCF out is kind of the end. Okay, we've talked about a difference of two squares problem. I think what's going to be crucial here is that you are comfortable identifying when numbers and when variables are perfect squares. Okay, perfect squares are numbers like 1, 4, 9, 16, 25, 36, 49, numbers that you could easily take the square root of and not get a decimal. Variables that are considered perfect squares are any variable whose exponent is even. So it would have to be x squared, x to the 4th, x to the 6th. Something like that would mean that that variable is also a perfect square. Okay. Now, quick refresher on how to factor the difference of two squares. First and foremost, we have to make sure that the factoring problem is a difference problem, so it definitely has to have subtraction in it. And then each of your two terms both have to be perfect squares. Variables have to have even exponents. Numbers have to be these perfect squares here. Okay, so here's an example. 25x squared minus 81. Okay. 25 and 81 are both perfect squares. I can see the exponent on the x is 2. It's even, so x squared is a perfect square, and it definitely has subtraction. If this was addition in between here, that would not be a difference of two squares. Once you've identified that it is a difference of two squares, then you're going to draw two empty sets of parentheses. You'll place an addition sign in the middle of one and a subtraction sign in the middle of the other. It doesn't matter which one. Okay. Then you will take the square root of the entire first term because everything should be a perfect square. So we're going to take the square root of 25, we're going to take the square root of x squared, and we get a 5x as our answer. The square root of the first term, that goes into the first spot in each set of parentheses. So you're putting that answer in the first spot of each set of parentheses. Then you take the square root of the second term, okay, square root of the second term, and you put that in the second spot of each set of parentheses. And then that would be your answer, 5x plus 9, 5x minus 9. Okay? All right, I'm going to circle back to C and D because these are the two new types of factoring problems. Just as a quick review, we talked about trinomials. This is when a trinomial, if the lead coefficient is in fact a 1, just make a little note to yourself here that if the lead coefficient is a 1, you can immediately draw two sets of parentheses. You can put an X at the beginning of each set of parentheses, and this is where you would draw like one of those little X charts and put A times C in the top and then B in the bottom. A trinomial where the lead coefficient is not a 1, this is when we do the factoring by grouping and we put the 4 blank lines, first term on first blank, last term on last blank, and then we make one of these X puzzles to help us figure out what goes on the middle 2 blanks. Finally, if you have more than 3 terms, like let's say that you have 4 terms, what you would do is you would pick up where you do factoring by grouping, where you would group together maybe the first 2 terms and the last 2 terms, pulling GCFs out of each group, okay, factoring by grouping. So let's go back and look at the 2 new ones here, okay? Our 2 new factoring problems, these are new, is a sum of 2 cubes and then a difference of 2 cubes, okay? So sum, we got addition there. Difference, we have subtraction there. Okay, so now we're talking about cubes. We need to make sure that we know, okay, what makes a number a perfect cube and what would make a variable a perfect cube? Well, a number being a perfect cube, some examples are 1, 8, 27, 64, 125. You know, you're probably less familiar with numbers that are perfect cubes, but if on your calculator you hit the math button, okay, and then after you've hit the math button, if you just choose option number 3, okay, that is the cubic root button. If you're ever not sure if a number is a perfect cube, then just take the cubic root of it on your calculator, and the answer should come out as like an integer or whole number. No decimals, no fractions. That would tell you, okay, that number is a perfect cube. How do you know whether variables are perfect cubes? Well, you look at the exponent, and if the exponent is a number that is divisible by 3, so you say, could 3 be divided into that exponent without any remainders? That means that variable is a perfect cube. So things like x cubed, x to the 6th, x to the 9th, x to the 12th, those would all be considered to be perfect cubes, okay? Now, you have to be able to identify whether the problem you're looking at is a sum or difference of 2 cubes. So sum, difference, that's easy. We know addition or subtraction, but you have to be able to look at your numbers and your variables and say, everything is fitting into that box of being a cube, a perfect cube. Okay, now if it meets that criteria, this is a little bit different. What you're going to do is you're going to, and I'm going to have you just kind of label this here. I know I have this written generically, but on the left side of this, the left side represents how the original problem looks, okay, original. Then the right side represents your factored answer, okay? So what's a little different about this is when you factor either a sum or a difference of 2 cubes, you'll notice that the answer is a binomial, but then it's a trinomial. And that's the case for both of these. In fact, if you look at the answer for difference of 2 cubes and sum of 2 cubes, you'll notice the variables are the same. Do you see how the binomial has an a, then a b? That's also true here, an a, then a b. Then the trinomial has an a squared as its first term. It has a b squared as its last term, and in the middle, it has an ab. Okay? This is something you're going to need to memorize. What is different, though, about a sum and a difference of 2 cubes is the signs that go in between. So I want to give you a little tip here for how you could maybe memorize this, because there is a pattern. If the problem is a sum of 2 cubes, then, and I'm going to give you this acronym. The acronym is SOAP, okay? Now, the S stands for same, meaning if your original problem is a sum of 2 cubes, then the sign that goes in the middle of your binomial should be the same sign, okay? If your problem is a difference of 2 cubes, then the sign that goes in the middle of the binomial should be the same as the original problem. It should be subtraction, Okay, the O in SOAP stands for opposite. Okay, opposite. So once you've put that initial sign in the middle of your binomial, the next sign that goes in between the first and second term in your trinomial is simply the opposite sign that you started with. So if you started with addition here, then this is going to be subtraction. If you started with subtraction, then the next sign in between the first and second term will be addition. Okay? And the last sign at the end, the last sign, and I'm just going to highlight this there and there, this is what the AP stands for, is always positive. Okay, so AP in SOAP stands for, the last sign is always positive. Okay, that's always the same. Okay, always positive. Okay, so let's put this into action. We're going to try to factor a sum of two cubes, and then we're going to try to factor a difference of two cubes. So first and foremost, we look at the problem, we say, is there a GCF that we could factor out of 125 and 64? The answer is no. So then I'm going to look closer at 125 and 64, and I'm going to say, well, are those numbers, are they perfect cubes? Again, if you're not sure, hit the math button, pick option 3, I believe it is, for the cubic root, okay, whatever the cubic root option is there. Let me just double check that. Okay, it might be option 4 actually, folks. Okay, it might be option 4, math option 4, okay? And you could try. Take the cubic root of 125, take the cubic root of 64. I think you're going to find that, yes, the cubic root of 125 is 5, the cubic root of 64 is 4. Those are both perfect cubes. So now I have to make sure, but is my variable a perfect cube? Well, to be a perfect cube, the variable, the exponent on the variable, which is a 3, has to be divisible by 3 without having any remainder. Well, sure, 3 goes into 3 once. So this is classifying as a sum of two cubes. Okay, so I'm going to go ahead and set the problem up. Here's how I like to do it. I like to draw a smaller parenthesis for the binomial, larger for the trinomial, and then I like to put in all the SOAP signs, okay, before I even fill anything in. So according to the SOAP acronym, my first sign in the binomial should be the same as the original problem. So if this is a sum problem, then I'm going to fill in addition. The O in SOAP is opposite, so my next sign is going to be the opposite of what I started. It'll be subtraction. And my last sign, AP in SOAP, always positive, so I put AP. Okay, so I've got that filled in. Now to fill in what goes in all these gaps. So I'm going to take not the square root, but the cubic root of my first term. And I'm just going to call that A, since that's how it's referenced here, okay? So if I do the cubic root of 125, I get 5, and the cubic root of x cubed, I get x. So my A is a 5x. Now let's look at our answer here. In the binomial, the first term is that A value. So I'm going to plug 5x there. Okay, I'm going to go ahead and write down what the B value is. B would be the cubic root of the second term. The cubic root of 64 is 4. So in the binomial, you put A first, and then we'll put B second. So I'm going to put the 4 here. Okay, now when I get to the trinomial, let's look at the way this is set up. A squared goes in the beginning, the first part of the trinomial. B squared goes in the back. A squared first, B squared in the back. Now be careful with this. If I take 5x and I square it, I'm going to do this up here off to the side, a mistake that a lot of people make is they write down 5x squared. But think about what that means. 5x squared means a 5x times a 5x. You need to make sure you also square the 5. Technically, this should be a 25x squared here. Okay, now I'm going to move all the way to the back. Now I'm going to take that B value, which was a 4. I'm going to square it. That means I'll have a 16 here. And then what goes in the middle of the trinomial? Well, let's look over here. It should be A times B. So if I take 5x times 4, that would be a 20x. Okay, and this would be my answer for factoring that sum of two cubes. Okay, you will never be able to factor this trinomial over here down further, so you don't have to worry about trying to look at that and say, oh, but that is now a trinomial that the lead coefficient's not a 1. If it was a sum or difference of two cubes, you're never going to be able to break that trinomial piece down further. Okay, so let's go ahead. We'll do this next one a little bit faster here. Our example is 8x cubed minus 27. That's why this is a difference. 8 and 27 both classify as being perfect cubes, and so does an x cubed there. So I'm going to set up binomial, trinomial. I'm going to fill in my signs. S in SOAP, same. This will be subtraction. O, opposite. AP, always positive. Okay, then I'm going to do the cubic root of 8x cubed. That means my A would be a 2x, and the cubic root of 27 would be 3. Again, you can just use the math option, option 4, I believe, if you're not sure what the cubic roots of those are. Okay, now I'm going to fill in 2x goes at the beginning of the binomial, 3 goes at the end. When I get to the trinomial, I need to be doing a 2x squared, which is a 2x times a 2x. That would be a 4x squared. In the back, I should be taking the b value, which is a 3, but squaring it, so that's a 9. And in the middle, the 2 get multiplied together. 2x times 3, we make that a 6x. Okay. All right, so now that we've talked through all of those types, let's go ahead and see if we can't just kind of work through some of these problems. I'm going to try to leave this box visible here so that we can look at all these. By the way, if you feel like there's nothing that you can do, there's not even a GCF that you could remove, then you're just going to write down that problem is prime. Okay, so let's take a look at example A and see what we can come up with here. Please remember, before you try to get the problem to jam into one of these types, we got to do this first part here. We got to check for that GCF. Okay, so we're saying, is there anything in these two terms that we see that they have in common? Well, 16 and 54, they both have a 2 that we could remove. Also, I'm noticing there's an x to the 4th and an x here. So x is showing up in both those. It looks like my GCF might just be a 2x. Okay, remember we've talked before about how when you factor out a GCF, you're really dividing what's there by what you're factoring out. That leaves me with an 8x cubed plus a 27y cubed. Okay, all right, so now with the GCF out, you can see how, okay, what we have in parentheses here, now let me look at my list and say, does an 8x cubed plus 27y cubed fit into any of these categories? Okay, well, when it's a binomial, it would be one of these first three, B, C, or D. These other ones are either trinomials or even bigger. Okay, so it's either going to be one of these three, or it's going to be type A, which is, I took out the GCF and then I couldn't do anything more. Okay, when I see these numbers here, 8 and 27, that makes me think that those are perfect cubes. Let me just skim over my exponents. These exponents are divisible by 3, so those are also perfect cubes. So that means that this problem right here, it's looking like it is a sum of 2 cubes. Okay, and you don't have to identify what type of problem it is. I'm just writing that there. Okay, so make sure you don't lose your GCF. Include the GCF there, but go ahead and let's set up the problem. If it is a sum of 2 cubes, then we want to create like a binomial and a trinomial. I'm going to think through the SOAP acronym. I'm going to S for same, then O for opposite, and AP for always positive. Okay, now I'm going to do the cubic root of 8x cubed. I'm going to write that off to the side, say my A is a 2x, and then I'm going to do the cubic root of 27y cubed. That would be 3y. Okay, I'm going to fill in A goes here, so that's 2x. B goes there, that's 3y. Then at the beginning of the trinomial is the A value squared. So 2x times another 2x, that's 4x squared. In the back of the trinomial is the B value squared. That's 3y times 3y. That should be 9y squared. And in the middle, it all gets multiplied together into a 6xy. And that is the answer. Okay? All right, let's take a look at example B. Example B. I'm looking for a GCF. I'm not seeing that there's any numbers or letters that I could remove from these, so there's no GCF. I'm going to go ahead and skim down here and say, okay, well, does this fit into any of these categories? Well, it's not option A, because I couldn't even pull out a GCF. It's not E, F, or G, because this is only a binomial. I see addition, so that eliminates the difference of 2 squares or the difference of 2 cubes. The only thing it possibly could be is a sum of 2 cubes. Let me look closer. The variables are definitely perfect cubes. 8 is also a perfect cube, but here's the one piece that's preventing this from being a perfect cube. It's that 5. That is not a perfect cube. It would need to have been a perfect cube in order for me to be able to call it a sum of two cubes. So I'm just going to call this prime. Okay, similar to example C, which I already called prime, you could check on your calculator by taking the cubic root of 400, and you would notice that 400 is not a perfect cube. Okay, let's jump on down here to example D. I'm going to check for a GCF. There's nothing I can remove. I'm going to look at my list and say, okay, well, it's not a binomial, so it's not those three. It's not a trinomial. In fact, it actually has more than three terms. So I'm going to use the tactic of factoring by grouping. You want to think of this as someone filled in 4 blank lines and then they kind of bailed on the problem. So you want to group together the first 2 terms. Make sure when you group the second 2 terms, you scoop the negative sign up inside the parentheses and just insert your own addition symbol. We're going to now pull a GCF out of the first group. And the goal is to pull a GCF out of the second group in hopes that what you would leave behind would be the exact same quantity that you left behind from the first group. Okay, so if I remove a -2 from each of these, it will change this into an x plus 5. Now I see these both have an x plus 5 in them, so I'm going to remove an x plus 5 from each of those terms, like it's a GCF here. Okay, so gone, gone, and that leaves me with x squared minus 2. Okay. Now, before I circle this, I should examine each of these 2 terms and say, now, could I do anything more with either of these 2 terms? Can't do anything more with x plus 5. Let me think about x squared minus 2. Okay, it's a binomial. I got a difference here. When I see an even exponent, I think, oh, that's a perfect square. 2 would have to be a perfect square in order for this to be a difference of 2 squares, and 2 is not a perfect square. If you take the square root of that, it's like 1.41. It keeps going on and on. So this is actually our final answer. Okay, all right, let's go ahead and try example E here. We're just going to look at a few more and then we will wrap this up here. In example E, I want to check for my GCF first. It looks like maybe a 5 could go into both 5 and 320. I also notice there is a y in both of those terms. So I'm going to pull out a 5y as my GCF. That'll leave me y cubed minus 64z cubed. I now want to say, okay, is y cubed minus 64z cubed a difference, because we got subtraction, a difference of 2 cubes? Well, the variables are perfect cubes. 64, I believe, is a perfect cube as well. So I'm going to go ahead, I'm going to keep the 5y there. I'm going to go ahead and make space here for a binomial and a trinomial. I'm going to use my SOAP acronym, same, opposite, always positive. I'm going to do the cubic root of my first term, write that off to the side, call that A. I'm going to do the cubic root of the second term, write that off to the side. That's going to be 4z is my B. And then I'm going to fill in what I said A was, which is y. Fill in what B is, that's 4z. Then here, this is the A value squared, so that's, whoops, that's y squared. In the back, I should take the B value and square it, so that'd be 16z squared. And in the middle, the A and the B get multiplied together for a 4yz. Okay, and that's my answer. Very important that you still have the 5y there. Okay, this one is a really interesting problem because it starts out as a difference of 2 squares, okay, where you do the plus and the minus and the square root of each. But then if you look closer, you notice that this piece right here is like another difference of 2 squares. Okay, so you find these problems where you start going down a little bit of a rabbit hole here, a rabbit trail, because just because you've done one thing doesn't mean that there's not more that can be done. So don't just automatically circle your answer. This piece here broke down as another difference of 2 squares. That's how I got x plus 5, x minus 5. However, there is no such thing as being able to factor a sum of 2 squares. So this piece just had to be carried down. I have 3 factors to my answer there. Okay, on the back, there is just one problem I want to look at with you here. Okay, and I just want to draw your attention to example A. You'll notice, wow, there were 6 terms there. Okay, and actually I'm going to use example C because we're going to just finish this one as our ending here. Okay, if you have more than 4 terms, we're going to assume that you're always going to be given a problem where it would be an even number of terms. So I'm going to have you group together the first half and the second half. Okay, so in this case, it'd be the first 3 and the second 3. Notice how I scooped the negative up inside the parentheses and put an addition sign. Okay, when we do factoring by grouping, we then examine for a GCF. You can see I've factored out an a cubed from those, a b, I think a negative b cubed actually from those, and now I had like this matching quantity right there that I then removed as my GCF, and that left me with this a cubed minus b cubed. Now this is what I was saying. Always try to look at what you have and say, is there anything more I can do with that to break it down further? Well, there's actually a lot. This first factor, that's a trinomial where the lead coefficient is a 1. So we could actually break that down. I could make an X puzzle and put 9 in the top, -6 in the bottom. And the two numbers for this would be -3 and -3. So that's how my trinomial factors. And then I look at this and I say, oh, that is a difference of 2 cubes. So it's actually the generic formula. I'm going to do SOAP. Same, opposite, always positive. If you do the cubic root of a cubed, then that makes AA. And if you do the cubic root of b cubed, that makes b. So it's a squared, b squared, ab in the middle. Wow, this is my final, this is officially, like, I've got it completely factored. Remember, when you factor a sum or difference of 2 cubes, this trinomial, you'll never be able to factor that anymore. So you don't have to try to say, oh, but this is a trinomial with a lead coefficient of 1. You won't be able to, like, solve your X puzzle. Okay, I believe